Hi there. Welcome to our video on exact differential equations, and this is going to be part one of those videos. Okay, so we're going to talk about differential equations of a certain form, and now we're going to be looking at what we call. Well, let me take you down, and you'll see what I mean, and we'll get going. All right, so exact equations. So we're going to be looking at differential equations of the form that you see right here. Okay, a function of x and y times dx plus a function of x and y times dy equals 0. All right, that's what we're going to be looking at. This is not necessarily exact yet. Okay, we're going to talk about what it means to be exact, but this is the form that we're going to be the form of differential equations that we'll be looking at in this section. Okay, now already you can see there's something different here. We've separated the dx and the dy. Usually we have a fraction involving those, and that means the derivative of either y with respect to x or x with respect to y. Here we've separated them out. Now, it's dangerous to do that unless you have a really good understanding of what you're doing, because that fraction dy dx stands for derivative. When you pull them apart, it's not so clear what we're talking about anymore. All right. Now, if you have a full understanding of what you're doing, you can make sense of these things, and if you can be careful about how you treat them. And the book is being careful, so we can trust what they're doing here. But I just want to caution you: don't think that you can always just pull these apart. You can run into trouble. All right, so don't run away with this thinking. Walk away from this thinking that you can always just pull these apart. Be cautious about that. This differential equation can be interpreted as the one below, or this other one below. How so? Well, if I multiply through this differential equation by dx, you'll see I get to the first one. And if I multiply the third differential equation through by dy, you'll see I get to the top one, right? So this is a way of writing down what they mean by this is really something of this form, where y is a function of x, or something of this form, where x is a function of y. So there, we've made sense of it in a rigorous way. That's what they mean when they write that, okay? Now, these differential equations, have we seen these? Well, we sure have. Some of the differential equations we've seen were actually of that form already. This is a differential equation that we could have come across if you had pulled the dx and dy apart. Notice we have a function of x and y times dx plus a function of x and y times dy equals 0. And again down here, function of x and y equals 0. Again, function of x and y equals 0. All right? Also, these are written in those other forms that we saw above. Function of x and y, function of x and y. And again, function of x and y, function of x and y. And so all of these are examples of equations. All 9 of these are examples of equations of the type we just talked about. Okay. Now, one thing that's really useful to note that they point out here is that a separable equation is of that form. So actually, any separable equation is an equation of that form. So separable equations are a special case, but we're looking at something a little bit more general. It's kind of a generalization of separable equations. Okay. Now, one thing I want to point out to you is let me skip ahead here. Okay, so yeah, one of the things I wanted to point out was that okay, so one other thing that's worth pointing out that they describe in the book is they start with an example here, and they look at a function equal to a constant. So they got a big function of x and y equal to a constant. And they want to show that that's actually a solution to this differential equation. All right, so we're kind of working backwards. We're starting with a solution, and we want to just prove that, yes, it is a solution to this differential equation. Well, how do you do that? Well, you learned in, I think it was in Calc 1, you learned how to implicitly differentiate. Implicitly differentiate means that you hold one of the variables constant and you differentiate with respect to the other one. But you have to keep in mind that the other one, maybe y, is a function of the first one. So you're going to treat y as a function of x, all right? And then you're going to differentiate through by, yeah, what I said was baloney. You don't treat one as a constant. Let me start over. Okay, so the next thing I want to look at here is an example of a solution to such an equation. Okay, so what we have here is we have a function of x and y equals a constant. Okay, function of x and y equals a constant, and they want us to show that that is a solution to this differential equation down here. This is the differential equation of the form we were just talking about. We've got a function of x and y times dx, function of x and y times dy equals 0, right? So how do we show that this guy is a solution to that equation? Well, the trick here is to use implicit differentiation. Implicit differentiation is something you learned in Calc 1, all right? It is a way of differentiating without solving for one of the variables first. You don't need to solve for a variable, you just differentiate with everything locked into an equation as we see here, okay? And we could implicitly differentiate with respect to x, treating y as a function of x, or we could implicitly differentiate with respect to y, treating x as a function of y. And that's what they did down here, right? First they did it with respect to x, and if you go back to your calculus notes, you'll see that is exactly what you would get if you differentiated this top equation with respect to x all the way through. And you can see the constant becomes 0 on the right-hand side. And you can see that this is exactly in the form of one of those of the differential equations that we're talking about today. You could have also thought of x as a function of y and implicitly differentiated that way. And you would have gotten, again, something of the form that we're talking about. And both of these are equivalent to, as we said before, this differential equation. And so that proves that doing it either way, right? Either this way or this way, you don't have to do it both ways. Either one of those proves that that is a solution to this differential equation. Okay. Now, what's the point of doing this? Well, the point of doing this is to point out this theorem here. Okay. This theorem says that if you have a function of x and y with continuous partial derivatives, and you have an equation f of x, y equals c, which is what we have right here, f of x, y equals c. If you do what we just did, right, you implicitly differentiate, you end up getting this differential equation, right? And so that means that this is a solution to this differential equation. So if we start with a function of x and y set equal to a constant, it is the solution to such an equation. Now this is exactly where the word exact comes from, okay? So exact means that the solution happens to come from such a function, all right? So if the differential equations of the form that we're talking about, if we can find that f, the capital F, and set it equal to a constant, if when we differentiate that, it gives us that differential equation, it's a solution to that differential equation, that's what it means for the differential equation to be exact. It exactly comes from this function f of x, y. And so what that means is not every differential equation of that form will come from such a function, right? If we're calling some of them exact, that must mean that those are the special ones, right? And that's the case. So not every one of these differential equations is going to come from such a function. But the ones that do are called exact. So let's go back. Okay. So that brings us to this theorem 2.5.2, which is a very important theorem, and it's going to tell us how to identify when a differential equation is exact without having to find the solution. Because, you know, if you have to find the solution to tell if it's exact, well, then what's the point? Because you're done. You found the solution, right? So we'd like to be able to tell whether or not we can expect to find a solution before we do it, right? And that's what this theorem is about. It tells us, just by looking at the differential equation, whether or not we can expect to find a solution. So let's read the hypotheses. It's called, by the way, it's called the exactness condition. So it's going to tell us when a differential equation of the form that we're talking about is exact. So suppose m and n are continuous and have continuous partial derivatives. So they took the partial with respect to y on m and x on n on some open rectangle. So that means some range, open interval in x and some open interval in y. So when you take an open interval x and y, you get a rectangle, right? So if they're continuous, not just at a point, the point of this is that they're not just continuous at a point, but they're continuous in a little box, okay? Then this differential equation is exact on that rectangle if and only if the partial derivatives are equal throughout the rectangle. So in other words, we can expect to find a solution if these partial derivatives are equal. All right, so that means that before we look for a solution, we should check this. Not only that, but this is if and only if, which means not only if there's a solution exists, yes, this is true, but also that's saying that if this is true, then a solution exists. So this means that's all we have to check. As soon as we check this, we know a solution exists. Okay? So let me take you down to the paper here, and I want to work you through an example. Okay? Okay, so what are we going to do here? This is going to be cut. Maybe I'll just stop it. Okay, so here's our example differential equation that I want to look at. Okay, so what we want to do is see if we can check it for exactness using the theorem, and then we'll even see if we can find the solution. Okay, so how do we use the theorem? Well, let's look at what the theorem says. The theorem says that if this equation is true, if my equals nx, then this differential equation is exact, so we can expect to find a solution. What are m and n? Well, m is the function next to dx. Well, that's this, right? So this right here is our m. What is n? N is the function next to dy. So that's this. So this is our n. And what is it asking us to do? Compute my and nx. All right, so we're going to compute my and nx. So I'd like you to pause the video now and compute these, and we will reconvene. All right, and we'll check our answers. Okay, so pause. 3, 2, 1. Okay, welcome back. Let's check our answers together. My, I'm taking the partial of this function with respect to y. Now, when I do that, I'm treating x as a constant when I do that. All right. Don't treat x as a function of y. Treat it as a constant. When you have a function of two variables and you take the partial with respect to one, treat the other one as a constant. Okay. So what do I get? I get 2y plus 3x squared. And what do we get here? We get 2y plus 3x squared. Wow, I got to move out of the way. Wow, they are equal, right? They are the same. They are the same. And so that condition of the theorem is satisfied. And so what the theorem tells us, if we check the hypotheses, let's check these hypotheses up here. So let me move out of the way again. Are m and n continuous? Well, these are polynomial functions, so yes. Do they have continuous partial derivatives? Well, these are polynomial functions, so yes. polynomials are continuous everywhere. So yes, okay, we should have checked that at the very beginning. But yeah, they are. So we can go from here to here. So this differential equation is exact. Okay. Now what's the open rectangle? Well, we can use any rectangle that we want as long as these functions are continuous on it. But these functions are polynomials, they're continuous everywhere. So we can just take that rectangle to be all everything from x from negative infinity to infinity and y from negative infinity to infinity. Okay, so this is no worries there. So what we've concluded here is that our differential equation is exact. Our differential equation is exact, and that makes us very happy. All right. Because that means we can expect to find a solution. Now, how would we go about doing that? All right. Remember when we looked at that other theorem. So let me pull this back down. All right. We had another theorem back up here that we looked at. What we're doing is we are comparing this differential equation that we have here to this one here. And this theorem says that this one came from this function. So what we want to do is run this backwards. Now notice, how did it come from this function? Well, to get this term, we differentiated our function with respect to x. So that's what m is. M is the derivative of the function that we're looking for with respect to x. All right? So that means, another way to say that is that f is the antiderivative of m with respect to x. Okay, but that's not the only thing we know. Look at the other side. This is fy, but what's that? That's n, right? So n is supposed to be the derivative of f with respect to y, right? So that means that f is the antiderivative of n with respect to y. So at the same time, f is the antiderivative of n with respect to y. Okay, so these are what we have to work with. Now, took that paper away too soon, what are m and n? Well, m is this function, right? So I'm going to anti-differentiate that with respect to x, right? So let's see what we get. And what's n? It's going to be this guy. I'm going to anti-differentiate that with respect to y. Okay? So what I'd like you to do is work these out. Do these integrals. In the first integral, you're treating y as a constant. In the second integral, you're treating x as a constant. Okay? So let's pause and reconvene and check our answers. Okay? So 3, 2, 1. Okay, welcome back. When you anti-differentiate this guy, you should have gotten y squared, let's put x on the front, xy squared plus x cubed y plus a constant. Now remember, we're treating y as a constant, right? So any function of y will be a constant. So let me put g of y here. And when we do this one, we're anti-differentiating with respect to y. We get xy squared plus x cubed y plus a constant. Now, we're treating x as a constant, so any function of x will be a constant. Okay? So, here's what we have. On the one hand, f has to be this. On the other hand, f has to be this. Are these compatible? Well, yeah. If g does not depend on y, if it actually is just a constant, c, and h does not depend on x, if it is a constant, say the same constant c, then these are equal. right? So these can be equal. And so we see that that's what our function has to be, right? Our function, f of xy, has to be y squared plus x cubed y. Now, I could write plus c, but we're going to be setting our function equal to a constant anyway. So if you have plus c on the left and plus c on the right, they subtract 1 from both sides and you still have a c. So it doesn't really matter. So we can just assume that this constant is 0. Okay? Can let this be 0 and that be 0. And so this works. And so actually the solution to this differential equation is the following thing. It's y squared plus x cubed y equals a constant. Right? And that solves the differential equation. And we ran it, we first checked that it was exact, right, by checking these. And then once we knew it was exact, we went through and anti-differentiated. Now you may have said, well, what's all that nonsense you were talking about, Professor Balawa, about these functions, because we just set them equal to 0 in the end. Well, that's not, you're not always going to set them equal to 0, because what's going to happen sometimes, and we'll probably look at an example, sometimes you will get an expression of x up here, and you'll get an expression of y down here. This g is needed to take account of that y, and this h is needed to take account of that x, all right? Or those x's if you've got some more complicated stuff. All right, so these are important. They won't always be set equal to 0, and we'll see that in some future examples. But we found the solution. So I'm going to end this video here, all right? And there's still some more tough stuff we want to talk about. I want to talk about the reasons why some of these theorems are true, and then I want to look at some more interesting examples. We'll pick that up in another video. Okay? So I'll see you in the next one.